Okay, so today we're going to be looking at the tangents, the velocity function, and other rates of change. We've talked about in the past the average rate of change. We've also talked about the instantaneous rate of change. And here's our first definition that we're going to look at today. It says that the tangent line to the curve at the point P is the line through P with a slope given as the following. The slope is found by taking the limit of f of x minus f of a over x minus a. Well, let's look at the graphical representation of this and see what that means. If I take a point, or here's my first x value, it's called a. And I go up to a curve, and on the curve, it has an ordered pair a comma f of a. Then if I go over to x, and I list the point, it's x comma f of x. Then if I connect the 2 points, what type of a line do I have? That's a secant line. How do I get the slope of the secant line? I just use a slope formula. Change in y over the change in x. So if I take the change in the y is the f of x minus f of a. That's where the top comes from. And then I take the difference in the x's, which is x minus a. That's where the bottom comes from. So the right-hand side is the slope of the secant line. Okay? Then what they do is they say basically what we're going to do here. Okay, so here's what we have. We have a secant line. And what we're going to do is we're going to take x and we're going to approach a. So we're moving this point down the curve. So moving it down the curve to get to that one point. Okay, we're taking the limit as x goes to a. And if I get to that one point, then what do I have as my answer then? I have the slope of the tangent line. Okay? So now in red, I have the tangent, which we are going to talk about in the next lesson, and that's going to refer to it as the derivative of the function. So the derivative, that's a differential calculus, that's a huge part of calculus, is to understand that that is your slope of the tangent line. This is one form of the derivative, a way that we write it. So we're taking a secant, slope of the secant, we take the limit as the x approaches the a, as these get really, really close to each other, to get to that one single point to calculate the slope of the tangent line at that point. Okay, so our first example that we see here says find the equation of a line tangent to the graph at the point 1, 1. It's always a good idea to get a visual of this though, so I'm just going to draw the graph. X squared is just a parabola. So here's my y equals x squared. And the point that we want to find the equation of the tangent line at is at 1, 1. So if I plot this point, here's the point 1, comma 1. That's when x equals 1. I'm trying to come up with a tangent line. So if I look at the definition from above, it says I need to take the limit as x goes to a of f of x minus f of a over x minus a. So the question becomes, is what is my a value in this case? 1. Okay, now I want to make sure I know which one it is. It's the first value is going to be your a. And then what's your f of a? Okay, now your f of a is the y value of this ordered pair. It just happens, it's a coincidence that the other one's also 1. But it doesn't have to be. They're not always going to be the same. In fact, most of the time they're not. But f of a is also 1. So now we plug it into the limit formula to calculate the slope of the tangent line. So to calculate the slope, in our case, we're going to take the limit as x approaches what? 1. Now what is my f of x? X squared, yeah. This is your f of x. F of x is your function. So it's x squared minus, what's the f of a again? 1 over x minus 1. If I take the limit of that expression now, as x approaches 1, then I will be able to compute the slope of the tangent line. So how do I compute this limit? What's the process I would take? Factor. So I'm going to factor it. I have x minus 1, x plus 1 over x minus 1. The x minus 1s drop out. After they've dropped out, then I use direct substitution, and I plug 1 in for the x. So I get 1 plus 1, which is 2. The slope of this tangent line then in red is equal to 2. That's the instantaneous rate of change at 1, 1. That's how quickly the rate of change of the graph is happening at that location. Instantaneous rate of change. It's also the slope of the tangent line. So now, if I use the slope, which is 2, and I have a point, the point is 1, 1, and I want to write the equation of the tangent line, then all I do is I use the point-slope form of a line, and I plug in the appropriate numbers. So it's already set up for us. We do y minus what? 1 equals the slope, which is 2, times x minus 1. And there's your equation. There's no reason to simplify it. You don't have to distribute. You don't need to add the 1 over. Just leave it like that. That's fine. So just make sure you really know point-slope form. It's y minus y1 equals m times x minus x1. You'll use this a lot when writing the equation of a tangent line. Okay, one of the concepts that we're going to see with the tangent line is we're going to talk about, you're going to see some things talking about local linearity. And really what we're doing, and this is going to be a question that'll come up, if we look at this graph of y equals x squared, and we go really close to this point right here, to 1, 1, the tangent line is going to be a really good approximation to the actual function itself. This tangent line is going to be almost identical, if I zoomed in really close, to the curve at 1, 1. So if I plugged in like 1.001, it's going to give me a really good idea of what the functional value is going to be. Now, for this equation, there's really no reason why we would want to do that. But there's other functions where we will use the tangent line to do a linear, what's called a linear approximation to the graph by using the tangent line. So this is something that will come up again later. So just be aware of that. So this kind of goes back and talks a little bit more about a different way to look at this idea. If I have a curve again, this time I start at A. And at that point, I have A comma f of A. That's just the general ordered pair on the curve. Well, this time, let's move over a distance of h. If we move over a distance of h, then the new x is going to be A plus h. And the ordered pair up here would be A plus h, comma, f of A plus h. So this is just a different way to figure out the slope. Now when you set up the equation, you're going to then subtract the two y's. So that's where the f of A plus h minus f of A comes up. And then you're going to subtract the x's. And what happens is the a disappears and you just get h on the bottom. Well, in order to get it down to a point, what has to happen to this distance that we call h? It's got to go down to 0. So that's why we take the limit as h approaches 0. And that is another way to compute the slope of the tangent line. It's just a different perspective. It's a different way to look at the graph. It's a different way to see what that's going to look like. It's going to start to pop up here. So we're supposed to find the equation of the line that's tangent to the graph at the point 3, 1. So here's our equation. Our f of x in this case is 3 over x. And I want to use this new definition right up here. So I'm going to take the limit as h approaches 0. So I start out with h approaches 0. Then what's my a in this case? 3. And what's my f of a? F of a would equal 1. So we have the a is 3. The f of a is going to be equal to 1. There's two ways to do this. We can put in the specific numbers if we have the point, or we can do it in general, okay? And I want to show you the general way because sometimes they don't give you the point at all. And they just want you to write what is going to be the equation or the slope of the tangent line in general. So in place of the a, we're just going to use x right now as my input. My x is my input. So I'm going to do f of x plus h. I'm going to write it like this. F of x plus h minus f of x all over h. And we're going to put the point in at the end this time. So if I want to get f of x plus h, what do? This is where the algebra comes in. I'm going to take the x plus h, and where am I going to put it? I'm going to put it in for the x in f of x. So that gets me 3 over x plus h. That's my f of x plus h. Minus f of x. What's our f of x in general? It's just 3 over x. And that's all over h. Now we have what's called a complex fraction. Complex fraction that we must simplify. So when we do this, we need to get common denominators up on the top. So what do I do to get a common denominator between x plus h and x? I multiply the two together. So I'm going to get x times x plus h. That's my common denominator. So with the first fraction, what do I have to multiply the first fraction by on the top and the bottom? X. So what's going to be the new numerator? 3x. Now with the second one, what do I have to multiply the top and the bottom by? X plus h. So it's negative 3 times x plus h. Now we are dividing by an h, or h over 1. That's the same as if I multiplied it by what? 1 over h. Okay? And that's what you'll usually do that when you're taking the limit in this fashion. So now I go to my next step. I'm going to take the limit as h approaches 0. I'm going to put these together then. And the 3x minus 3x, that disappears. Because 3x minus 3x is 0. I still do have a negative 3h on the top times 1 over h. Now, before we can use direct substitution, what's going to happen to this fraction then? What's going to drop out? This 1h drops out. And then I have negative 3 on the top. And what do I put in for the other h? 0, because h is going to 0. So now we end up with just an x squared on the bottom. So we get negative 3 over x squared. Now that expression is the slope of the tangent line anywhere on the graph. So this is the negative 3 over x squared is your general slope anywhere. Now at 3, 1, what do you think we would plug into this equation? the x, which is the 3 in this case. So we would have negative 3 over 3 squared. So negative 3 over 9, which is negative 1/3. Negative 1/3 is our slope at that point. Now, once we get the slope, we can use the point slope form of a line to write the equation of the tangent line. So now all we do is we write y minus what? 1 equals the slope, which is negative 1/3 times x minus 3. And there is the slope of the tangent line to the graph of 3 over x at the point 3, 1. What we're going to find is that we need to begin to generalize the idea of a tangent line to curves. Most important part of the difference quotients that we've used to find the slope of the tangent is the change in y over the change in x. That's the slope of the secant line. This is like your secant. And then we took the limit to get to the actual tangent. So this part here is like your average velocity. Your average velocity, we started with that. And then as we got closer to that one specific point, we got to the instantaneous rate of change by taking the limit. Let's see here. And this is kind of reiterated on the next page then, or one of the last pages here. We have almost the same diagram that I had earlier, where we have the 2 points, a, comma f of a, and a plus h, comma f of a plus h. The slope of the blue line, and the blue line, remember, that's our secant, is found by this equation right here. And that's the average velocity, average rate of change. That's your slope of your secant line. When we take the limit, then as this h, this distance, goes to 0, then we have the instantaneous velocity, or the slope of the tangent line. So this is our tangent line. All we're doing here is we're seeing it worded differently in relation to velocity and position. Instantaneous velocity and average velocity. Be sure you know the difference between the instantaneous and the average velocity. Remember, instantaneous velocity is for the slope of the tangent line. Average velocity is your slope of the secant line. And then we will talk about different applications of the rates of change, dealing with, like in physics, the rate of change of work with respect to time. Chemistry, biology, rate of change of population with respect to time. That's going to be, we can talk about average rate of change, or we can talk about an instantaneous rate of change. Just depends if you want the slope of the secant line then, or the slope of the tangent line. So we'll see that. All of these rates of change can be interpreted as a tangent line problem, so we can generalize it to this definition. Now this definition right here, again, it's a different way to write the same thing that we've seen before for the tangent line. In this case, we have 2 points, x1 and x2, change in y over the change in x, as the difference, or as the two x's get closer together. So as the x's get closer together, we take the limit. That gets us to a tangent line. This is really familiar to the property where you take the limit as x goes to a of the f of x minus f of a all over x minus a. That is the form that this is closest to. Almost identical, basically, is what we're talking about there. So we have 2 forms to find the slope of the tangent line. One of them where the x approaches a, and the other one is when what? H goes to 0. So there's 2 different forms, and we want to be familiar with both. And we're going to find out when we go into the next section, like tomorrow, looks exactly the same. Because it is the same. The derivative is your slope of the tangent line. We'll talk about that tomorrow.